This is a video about ionic bonding. Part 1, all about ions. Why ions form, how ions form, and what type of ions form. To start out with, a quick review of some terminology. Remember that groups on the periodic table are the vertical columns. These groups are numbered 1 through 18. Periods on the periodic table are the horizontal rows, and I've numbered the rows here 1 through 7. The term ion refers to an atom that gains or loses electrons to attain a charge. A cation is also known as a positive ion. This is formed when an atom that's neutral loses electrons. For example, Na1+ is a sodium 1+ ion. It forms when sodium that normally has 11 protons and 11 electrons loses an electron so that it only has 10 electrons. With 10 negatives and 11 positives, there's one positive charge left over, and that's indicated with the 1+ in the upper right-hand corner of the symbol. An anion is another term for a negative ion. Atoms gain electrons when they form anions. For example, Cl1- forms when chlorine, a neutral atom with 17 protons and 17 electrons, gains an extra electron so that it has 18 electrons. With 18 negatives and 17 positives, we have one negative left over, and that's indicated by the 1- charge in the upper right-hand corner of the symbol. Positive ions are named with the element name, so we call this Na1+, the sodium ion. Negative ions are named with the element name, but we change the suffix to IDE. So we don't call this a chlorine ion, we call this a chloride ion. Atoms form ions to become more stable. That's why they form. Stability is something that just happens in nature. So for example, if you were to drop this pen, you'd see that it hits the table and stops. Or if you were to try to balance the pen, it would fall over and it would stop moving once it becomes more stable. Elements do something similar, and we're going to take a look at that with the group 18 elements, noble gases. These are the most stable elements. They actually don't have to do anything to be stable because they already are. So what makes noble gases stable? Well, consider these are the noble gases: helium, neon, argon, krypton, xenon, radon, and the recently discovered oganesson. The first thing you might notice right away is that helium is a little bit of an outlier here. Helium has no 1p sublevel, so we don't have electrons in the 1s and 1p position because the 1p position doesn't exist. And we can see that with a quick look at a diagonal rule. In the quantum mechanics model of the atom, 1s fills in, and then 2s fills in with electrons. There is no 1p sublevel. So outside of helium, you can see that all of the other noble gases end with S2p6 in their outermost energy position. So neon, 2s2, 2p6, argon, 3s2, 3p6, krypton, 4s2, 4p6. And with some of these larger noble gases, we see that there are some d electrons and sometimes even some f electrons that get in between the s and the p electrons on the outside. But nevertheless, the outside electrons in the outermost energy level, for example with xenon here, end with s2p6. So there's something special about s2p6 that's making noble gases stable. Let's go ahead and give those s and p electrons on the outermost energy level a name. They're called valence electrons. The word valence means outside in Latin. These are the outermost s and p electrons in, or the outermost s and p sublevel electrons in an atom. We have a thing called the octet rule that we use. A duet is a group of 2, and a quartet's a group of 4, and octet is a group of 8. It turns out that atoms are most stable when they have 8 valence electrons. We can see that with noble gases. And elements that are not noble gases will have atoms that gain or lose valence electrons to form ions with 8 valence electrons, so that their outermost energy level position has S2P6 filled up. So let's take a look at how that works with sodium as an example. Sodium is element number 11. That means that it has 11 protons in the nucleus, and when it's neutral, it has 11 electrons in the nucleus. The electrons are in the 1s2, 2s2, 2p6, and 3s1 location. This is the quantum mechanics model. It's an electron configuration. And the quantum mechanics model is actually not something easy to draw. So let's take a step back and take a look at a Bohr model or a planetary model of the sodium atom. So we can see that there would be 11 protons in the nucleus, and the first 2 electrons, that would be 1s2, occupy that first energy position, and the next 8 electrons, 2s2 and 2p6, occupy the next energy level. That would be those electrons in the 1s and 1s position, 2s position, and 2p position would be considered core electrons, because outside of that, on the very outside of the sodium atom, in energy level 3, there would be an electron, and that would be the valence electron occupying the 3s1 position. Now in this picture we see that there are some other potential energy levels out here that go all the way up to 7, but a sodium atom, when it's neutral, wouldn't have those occupied at all. Now the nice thing about the Bohr model or the planetary model is that you can see the layers that exist within the atom, and you can see that energy level 3 is being shielded or blocked from attracting the nucleus with the electrons out there by the core electrons, that's what these are called, in between. So the lower energy level electrons shield the higher energy level electrons from attraction to the nucleus. That's known as the shielding effect. So within this Bohr model, we can see that there's some shielding going on. So what sodium tends to do is get rid of that 3s electron that's hanging out there. And when that happens, what we see, and let's just take a look at these side by side, a sodium atom and a sodium ion. What we see happening here is that sodium loses the 3s1 electron. When it does so, it has an electron structure of 1s2, 2s2, 2p6. There's our octet, 2s2, 2p6 on the outside. That means sodium has 11 protons and 10 electrons, and that would give it a 1+ charge. Now notice that that's isoelectronic to the neutral neon. Neon has 10 protons and 10 electrons. So that's a new term. Isoelectronic means same electron configuration. The term iso means the same in Latin. Turns out that ions are stable when they are isoelectronic to a noble gas. So let's go ahead and take a look at that sodium again and see that the sodium ion is isoelectronic to neon. It has the same electron structure. Notice that neon has 10 protons in the nucleus, sodium has 11 protons in the nucleus. So we have to be careful. These are not the same exactly. They do have different identities, but their electron structures are similar. So just as neon is stable when it ends with S2P6, so is sodium. Consider another atom, chlorine, and let's go back to our Bohr model with chlorine. Now, if we're dealing with chlorine, we have to be careful that we adjust the nucleus. It doesn't have 11 protons when it's chlorine, it has 17 protons. We need to add some protons in there. And we have to add a few more electrons. Chlorine, when it's neutral, has 17 electrons. It goes all the way up through 3p5. So 1s2, 2s2, 2p6, 3s2, and then 3p5. Now, chlorine could do the same thing that sodium did, I guess. You could take these electrons away on the outside, but you'd have to take away the 3s2 and the 3p5 electrons. That's 7 electrons. It turns out it's a little bit easier, a lot easier, I guess, for chlorine to become stable by, rather than taking those electrons away, gaining an electron. So this becomes 3p6. Now when that happens, we end up seeing that chlorine forms Cl1-, chloride ion. Notice it has 17 protons, and now it has 18 electrons with a 3p6. It's isoelectronic to argon. That's a neutral noble gas. that also ends with S2P6 in energy level 3. Notice the electron structures are the same. Now, chlorine stops changing at that point, because if we go back to the Bohr model, if we put 6 electrons here, it's full. The next electron that we would attempt to put on to a chlorine would have to occupy the next energy level out, and that means more shielding would occur. Again, we can see that in the diagonal rule. After 3p6 fills up, we'd have to start energy level 4. In fact, in the diagonal rule, you can see that after every S2p6 position fills, another energy level begins. After 3s2, 3p6, 4s begins, and after 4s2, 4p6, 5s begins. That's why the octet rule works, or that's why it's in place, because atoms are most stable when they have s2p6. They have maximized the negative on the outer layer of the atom, and that means that it's going to pull as tightly as it can to the nucleus without having to start another layer and have more shielding. So let's take a look at how this works for all of the elements in period 3 on the periodic table. That's Na, sodium, then magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. P, phosphorus, starts with pH in the name. That's why that's a P there. All right, so here we go. These are the period 3 elements, and I have their electron configurations written out. Notice that for sodium, and we already talked about this one, it loses this outermost electron and it forms a 1+ ion. Now it has 11 protons, and if we count these up, that would be 10 electrons. If we go across to the next element to the right, that's magnesium. We're talking about moving to the right here across period 3, and we're going to continue to move across period 3. Magnesium has 12 protons. If it loses these 2 electrons, it's going to form a 2+ charge. We can see that there's a total of 12 protons and now 2, 4, 10 electrons, just like sodium has. But if we focus on the octet, the outermost energy level S and P electrons, we can see that we have an octet here and we have an octet here for these elements. In fact, losing electrons is a way that a lot of elements form ions, by forming octets. So if we lose these electrons, the 1 electron there and the 2 electrons there, that's 3 electrons taken away. We get a 3+ charge on aluminum. If we do the same thing for silicon, lose these 2 electrons and these 2 electrons, it forms a 4+ ion. Now, what makes it more reasonable that silicon would lose 4 electrons? Because it could also gain 4 electrons there, right? If it gained 4 electrons, it would become Si 4-. It would go from 1s2, 2s2, 2p6, 3s2, 3p2. Now, to get that 4- charge, we would take that neutral silicon and make that, wouldn't change the s electrons around there, we would change the p electrons. We would add 4 electrons on to the outside of that atom. So instead of ending with 3s2, 3p2, it would end with 3s2, 3p6. And that's where it would get its 4- charge. It turns out that elements in group 14 can form both positive and negative ions. And silicon's in that group 14. Now, phosphorus ends with S2P3 on the outside. It could take those 5 electrons away, but it's actually easier to gain 3. If we add 3 onto the 3 electrons we have, we end up with 3p6, and that forms a 3- ion. Notice 15 positives in the 15 protons in the nucleus, and then 2, 4, 10, 12, 18 electrons. 15 positives and 18 negatives would give us a 3- charge. And notice we have an octet here. Notice that all of these elements so far have an octet. When we take a look at sulfur, that's the next element over in period 3, it ends with 3s2, 3p4. Rather than losing s2p4, that's 6 electrons, it gains 2 electrons and becomes s2p6. So when that happens, we get an octet, and we get a 2- charge because we added 2 extra negative electrons on there. Chlorine, when it's neutral, 17 protons, 17 electrons. On the outside, it ends with S2P5, so it gains 1 electron, becomes S2P6. That 1 electron gives it a 1 minus charge. Remember that these negative ions have an IDE ending, so this becomes phosphide, this becomes sulfide, and this becomes chloride. And notice that argon already has an octet down here. So it's not going to change at all. It's going to stay the way it is. It's already stable. You can see that all of these elements are isoelectronic when they form these particular ions. And those are all isoelectronic to the noble gas argon. You can notice up here that all of these elements are isoelectronic. Oops, I guess I skipped this one down here. This is also isoelectronic, that 3s2, 3p6. All of these elements are isoelectronic to each other. And they're also isoelectronic to the noble gas that comes before sodium. That's neon. Neon is element number 10. And its electron structure is 1s2, 2s2, 2p6. Notice how all of these end with s2p6 in energy level 2, and all of these end with s2p6 in energy level 3. So these ions form, becoming isoelectronic to the noble gas neon, and these ions form, becoming isoelectronic to the noble gas argon. Now, what about the other elements? We looked at elements in period 3, but the other elements on the periodic table can, many of the other elements can also be predicted. We need to take advantage of the fact that elements in the same group have similar outermost electron configurations. That means they have the same valence electrons. Let's take a look at how that works with the elements of group 1, the first group on the periodic table, from hydrogen all the way down to francium. I have those elements, electron configurations written out here, and what I'd like you to notice is that each one of these has the electron positions identified for all the electrons within the atom. Hydrogen has 1 electron, it's in the 1s position. Lithium has 3 electrons, 1s2, 2s1. All the way down to cesium has 55 electrons, 1s2, 2s2, 2p6, and so on, all the way through 6s1. And what we can see right away is that all of these group 1 elements end with s1. They have 1 valence electron. Now, we took a look at what happens with sodium that has 1 valence electron. It loses that valence electron and forms a 1 plus ion. So we can predict that all of the elements with group 1 that are in group 1 are going to do the same thing. They're going to lose that electron. When hydrogen loses its only electron, it has no electrons when it's a 1 plus ion. Lithium loses its outermost s electron and forms a 1s2 structure with a 1 plus charge. Now, these are violations of the Octet Rule, or we could call them exceptions to the Octet Rule. Normally, we would expect elements to end up with 8 valence electrons when they form ions. But when elements are really tiny like this and they have very low numbers of electrons, remember there is no 1p sublevel, so they are exceptions to the Octet Rule when they form ions. For the rest of these elements, we can see that octets are being formed, right? There's an octet. There's an octet. Let's see, 5s, got to take that electron away and form a 1 plus there. Take away this 5s1 electron, make a 1 plus charge, and here's the octet. 4s2, 4p6. Now, there are some d electrons in between there, but that's okay. Take away this outermost electron on cesium, form a 1 plus ion, and we see that here's the octet, 5s2, 5p6. And then for francium, we take away that electron, and we see that there's a 1 plus charge. So that would be an octet with 6s2, 6p6. Outermost energy level is 6 here. Now I know there are some energy level 4 and 5 electrons that are layered in on that atom, but the outermost energy level is energy level 6. So we don't have to go through and write out electron configurations and do this type of an analysis for at least the representative elements. The representative elements can be predicted. These are elements in groups 1 and 2 and 13 through 18. So if we look at this periodic table, we can see that the representative elements are the elements in these first two groups, and then groups 13, 14, 15, 16, 17, 18. These are the representative elements, all these and all these. Elements in the middle part of the table are called transition metals, and elements on the bottom are called intertransition metals. So for the representative elements, we can take advantage of the fact that elements within a group are similar, and ion charges can be determined based on which group the elements belong to on the periodic table. All the other elements, the transition metals and the intertransition metals, have ion charges that are determined by experiment. So we actually take a compound, break apart the compound into its elements, do an analysis of the mass, and then determine what charges had to be involved, what kind of ratio of those elements had to be there. Now, if we look at a periodic table, we can say that everything in group 1 is going to form a 1+ charge. Everything in group 2 is going to form a 2+ charge. Remember that the elements in this part of the table are determined by experiment. Now, you can think of it that these elements all have d electrons on the outside, and the elements in the intertransition metal part of the table have f electrons on the outside. And when d and f electrons are on the very outside of the atom, it muddies the water a little bit and makes it difficult to make predictions. So, for example, if we look at copper, we can see it forms a 1+ or a 2+ charge. We know that through experiments that we've done with copper. If we look at silver, it forms a 1+ charge only. And if we look at gold, that's Au, it forms a 1+ or a 3+ charge. So there's no pattern that we could use to predict the charges of these elements. Again, they have to be determined. Those charges are determined by experiment. Moving on to the rest of the representative elements, though, we can predict that elements in this column, that's group 13 on the periodic table, are going to form a 3+ charge. The elements in this column can both form a 4+ or a 4- charge, and then these elements form a 3- ion, these elements form a 2- ion, and these elements form a 1- ion. Now, those are the most common ions we might find. That's not to say that there can't be other ions that maybe would form. For example, if you look at Pb, which is lead, it's right here. It looks like when it's positive, it would form a 4+ charge. Now, somewhat unexpectedly, we know this by experiment, lead can sometimes form a 2+ charge as well, so it's 2+ or 4+. So what we see on this reference sheet is that you can look up the results of the experiments that have been done through the years and written down in different reference locations, and this is just a reference sheet. And this is not a complete listing of all the elements that are not in the representative part of the table. It's just an example of different common elements. This is common formulas for various ions. And what we can see on this sheet is that sometimes elements do the unexpected, like lead, and other elements are part of the table where we can't make predictions very easily, so we just have these written down so that we can look up the charges of those elements. We're going to use that moving forward as we start to learn more about ionic bonding. If you understood what we did here today, you should be able to write electron configurations for the ions, not the neutral atoms, but rather the ions of all the elements in period 2, or row 2 of the periodic table. That would be lithium, which would form a 1+ ion, beryllium would form a 2+ ion, boron 3+, carbon could be 4+ or 4-. Please make sure that you write out both of those electron configurations. All group 14 elements can be 4+ or 4-. Then nitrogen forms a 3-, oxygen forms a 2-, and fluorine forms a 1- charge. Again, period 2, lithium 1+, beryllium 2+, boron 3+, carbon 4+, and carbon 4-, nitrogen 3- or nitride, oxygen 2- or oxide, and fluorine 1- or fluoride. And by the way, carbon 4- would be called carbide. All right, good luck.